thank you for introducing me. Before I start, I would like to thank the organizer for organizing this nice event and giving me the opportunity to speak. I also want to mention that some concepts and notions I'm going to use were already introduced in previous talks, so I hope you don't mind the overlap. Okay. And similar to the talk before, I'm also going to talk about two-dimensional Dirac operators with delta potentials. However, I'm going to focus on a different aspect of it, namely the approximation of Dirac operators with delta potentials supported on the straight line. So let me start by giving a short outline of my presentation. First, I'm going to talk about Dirac operators in general, and this might overlap with Markus' talk. Then I'm going to introduce Dirac operators with delta potentials and Dirac operators with strong localized potentials. Afterwards, I'm going to mention a few known results connecting those two types of operators. And then I'm going to state a new approximation theorem for Dirac operators with delta potentials supported on the straight line. So that's the plan. The first operator I'm going to introduce is the free Dirac operator. It's given by minus I times sigma times the gradient plus m times sigma free. And its domain is H1 on R2. So m is again a constant which represents the mass. And we can take m in R because for the analysis it doesn't matter. Sigma times the gradient is again the same expression as Markus used. And the matrices sigma 1, sigma 2, and sigma 3 are the Pauli spin matrices. And this operator is used to describe relativistic spin 1/2 particles without any outer influence. It is well known that this operator is self-adjoint in L2 and that its spectrum is absolutely continuous and given by the interval from minus infinity to minus the absolute value of m, and the interval from the absolute value of m to infinity. Okay. So having introduced the free Dirac operator, I'm going to introduce the next Dirac operator, the perturbed Dirac operator, and we define it by D0, the free Dirac operator, plus eta times I2, where I2 is the 2 times 2 identity matrix. Plus tau times sigma 3 times V. Okay, we call eta and tau the interaction strengths, and they are numbers in R. And V is a real valued L infinity potential. Here the term eta times I2 times V is responsible for electrostatic fields, and the term tau times sigma 3 times V describes Lorentz-scalar fields. Okay. So now it's relatively easy to prove that dV is again self-adjoint and its domain is the same as the domain of the free Dirac operator, namely H1. However, one cannot really much say explicitly about the spectrum of this operator. So if one is interested in potentials which have very large values around the zero measure set and very low values everywhere else, then one can replace, or one often replaces, the potential V by a so-called delta potential. And this should simplify the spectral analysis of it. So in this vein, I'm going to introduce the Dirac operator with a delta potential. So we have here formally D0 plus eta times I2 plus tau times sigma 3 times the delta potential, and I take the delta potential supported on the straight line. So we have no broken line, but a straight line. And if I define omega plus and omega minus to be the positive and the negative open half space, I can rigorously define the operator by setting its domain to the set which contains all functions f in L2, such that the restriction of f to omega plus and omega minus is again in H1. And f has to fulfill certain boundary conditions on the slide. So if we set eta to 0, this condition is the same as Marcus had before in a slightly different form. Sorry? T, oh, sorry. Yeah, T is the trace operator. T is just the trace operator which maps the functions to the real line. Okay. Yeah, sorry. And again, the action of the Dirac operator with delta potential is given by minus I times sigma times the gradient plus m times sigma free applied to f restricted to omega plus, and the same for omega minus. So a unperturbed Dirac operator on omega plus and on omega minus. And in this situation, it is well known that this operator is self-adjoint if d is not equal to 4, where d equals eta squared minus tau squared. If d equals 4, one somehow has to change the Sobolev index here in order to get self-adjointness. And the case d equals 4 is also called critical case in literature. So that's important. Okay, and as I already said, such operators are seen as an idealization for Dirac operators with strongly localized potentials. And in order to justify this viewpoint, one has to prove approximation results. And therefore, I'm going to introduce a sequence of strongly localized potentials in the following way. So we define V epsilon of x1 and x2 to be Q of x2 divided by epsilon, where epsilon is a small number bigger than 0, and Q is an L infinity potential which has support in the interval from -1 to 1, and it should also be normed to 1. Okay. So we see that in the first direction, in the x1 direction, the function is constant, so that's the direction of the straight line, so to say. That's this direction. And in the second direction, the function V epsilon looks like the one depicted on the slide. And if epsilon goes to 0, the support of this function shrinks, and the peak of the function rises. So in the limit, we get, at least in a distributional sense, really the delta potential supported on the straight line. Okay. And this leads me to the definition of Dirac operator with strongly localized potentials. So again, the same definition as before. And as V epsilon is a L infinity function, we know again that dV epsilon is self-adjoint and has domain H1. So the answer, the question we want to answer is, of course, does dV epsilon converge to d delta? And at first we have to find a suitable sense of convergence, because these are, of course, unbounded operators and have different domains. So one defines the following two senses of convergence. Olaf Post already talked about it today, but I'm going to repeat it. So we say that a sequence of self-adjoint operators, d epsilon, converges to a self-adjoint operator T0 in the norm resolvent sense, if and only if the difference of their resolvents converges to 0 in an operator norm. And this leads also to a spectral implication. So for instance, if lambda is in the spectrum of the limit operator, then there exists a sequence of lambda epsilon in the approximating in the spectrum of the approximating operators, such that lambda epsilon converges to lambda, and the reverse implication also holds. And one can think of it that the spectrum cannot suddenly expand in the limit case and also cannot suddenly shrink in the limit case. Okay. This sense of convergence leads also to the convergence of some projection operators and so on. A weaker sense of convergence is the so-called strong resolvent convergence, where we only have strong convergence of the resolvents. Okay, and this leads also to weaker spectral implications. For instance, the equivalence from above becomes implication from left to right in a stronger Solent convergence sense. Okay. Now let me come to the known results. And the first thing one notices when one reads papers in this area is that if dv epsilon converges to some delta operator in a resolvent sense, then it does not converge to the Dirac operator with delta potential and the same interaction strength, but to a Dirac operator with delta potential and scaled interaction strengths, which I call eta tilde and tau tilde. And the scaling factor depends on d, where d is again eta squared minus tau squared, and has the following form: 2 times the tangent time of the square root of d divided by 2 divided by the square root of d. And if d goes to minus infinity, this scaling factor converges to 0. For d equals 0, the scaling factor is exactly 1. And for positive t, there are some singularities, and the first singularity is at pi squared. Okay. So in 1D, the natural counterpart to our situation are point interactions. And their substantial contributions were made by Scheber and Hughes. And moreover, Tuschek was able to use the results and prove norm-resolvent convergence for all d not equal to 2k plus 1 squared times pi squared. And these are exactly the singularities of the scaling factor. So there we have a quite complete picture. And in 2D, there exist, to my knowledge, only 2 results, both regarding strong resolvent convergence. Bernd, Holzmann, and Tuschek were able to prove strong resolvent convergence under the same assumptions as above for delta potential supported on the straight line. And Casano, Lotarajczyk, Maas, and Tuschek were able to prove the same for delta potential supported on compact and closed curves. Okay. In 3D, Maas and Pizzicillo were able to prove strong resolvent convergence under certain smallness assumption regarding the interaction strengths eta and tau. And where the delta potentials are supported on compact surfaces in 3D. Yeah. So to summarize, in 1D, the situation is pretty clear and not really much is to do. And in 2D and in 3D, there exist only a few results and no result regarding norm-resolvent convergence. So as a first step in proving norm-resolvent convergence results, we considered the Dirac operator with delta potential supported on the straight line. And we got the following result. So if d is smaller than pi squared divided by 4, and eta tilde and tau tilde are the scaled interaction strengths, then for all r in the interval from 0 to 1/2, there exists a c bigger than 0, such that the norm of the difference of the resolvents can be bounded by c times epsilon to the power of r. Okay. Yeah, in particular, dv epsilon converges to d delta in norm-resolvent sense. So we have norm-resolvent convergence, and we have even a rate of convergence. However, we still have the restriction on d. Okay, and in order to discuss this theorem, let me formulate 2 corollaries. And here we want to answer the following question. So which Dirac operators with given interaction strengths can we approximate? So we fix now the limit operator, and we look for eta and tau such that the sequence of Dirac operators with strongly localized potentials converge. So we ask the question from a different direction. So we fix this operator, and we are asking if there exists a sequence of Dirac operators with strong localized potentials that converges. And the answer is the following. if d tilde is in the open interval from -4 to 4, then there exists such eta and tau in R such that dv epsilon converges to d delta in normal solid sense. So in this area, we have a positive result. We were able to extend this result in some sense. Namely, if we assume that d tilde is not in the closed interval from -4 to 4, then we can find eta and tau in R such that not the Dirac operator with strongly localized potentials converges, but unitarily transformed Dirac operators with strongly localized potentials converge to this operator d delta. So also some kind of a positive result in this setting. So there remain the two cases, d tilde equals plus and -4. Let me comment on the case d -4 at first. And I just want to say that it's somehow clear from the rescaling that one cannot include the case d tilde equals -4. So it's more like a mathematical consequence than a mathematical problem that we couldn't include d tilde equals -4. Okay. There one has to go to other operators or some other Dirac operators with strongly localized potentials to get convergence. The case d tilde equals 4 is the so-called critical case. I already mentioned that. And in this case, Dirac operators with delta potentials are in general harder to analyze, and this also applies to the approximation. So this case is still open. Okay, and now I want to give some insight in the proof. And we started by finding two comparable resolvent formulas. Both of them are known in literature and are not in that sense new. Let me say something about the components of these resolvent formulas. So we have the free Dirac operator in here. Then we have the function Q here, which we used when we defined the strongly localized potentials. They play a secondary role. And then we have the A, B, and C operators here. And these are bounded operators in some L2 space given here. And one can see them somehow roughly said as shifts of certain known integral operators connected to the Dirac operator. Here, this is tilde, and I was going to say that, and this is the real eta. So, so this is the scaled version, and this is the unscaled version. So the scaling happens between here. Let me say that. Yeah. So that's right. So we have here eta and tau. So we really can compare these two formulas. Here we have eta tilde and tau tilde. One has to take care of that, but that's the right way. Yeah, and when proving convergence, one has to guarantee two things. The first thing is one has to guarantee that this operator is somehow uniformly bounded and doesn't explode. So this is really technical, and this is also where our restriction on D comes from. We had the restriction D has to be smaller than pi squared over 4, and this is exactly where our restriction comes from. And then one has to prove convergence results regarding the A, B, and C operators. And there we use the following technique. So I already said that they are somehow shifts of certain known integral operators. And we know mapping properties of these integral operators with respect to Sobolev spaces. So we somehow had to change our spaces where the A, B, and C operators live. And the first step was that we went from the classical L2 space to a Bochner L2 space with values, again, in an L2 space. But to incorporate the Sobolev regularity, we had to, again, change to an L2 HS space. And this really allowed us to use known results of certain integral operators to prove convergence results. And this is the new idea. And before I end my presentation, I want to stress that this idea is rather general, the idea regarding the convergence of A, B, and C, and can be applied in more general settings, for example, when the support of the delta potential is not necessarily the straight line, but a curve or a surface in 3D. So that's the natural next step, and we are working on that. Okay. That's all from my side. Thank you for your attention, and if there are any questions, I'll be happy to answer them.